Imagine a column of fluid performing a perfectly synchronized dance. It is simultaneously spinning in a circle while steadily rising upward. This specific type of movement is known as helical flow, or more intuitively, a corkscrew motion. In this scenario, every single particle follows a path that spirals around a central vertical axis. The stability of the flow. The first remarkable feature of this fluid is that it is divergence-free. This means that the fluid is incompressible. As it moves, it neither bunches up nor thins out. For every bit of fluid that enters a specific region, an equal amount must leave, ensuring the total volume remains constant throughout the motion. Local spin. The rigid body paradox. To understand how the fluid behaves on a microscopic level, we look at its vorticity, which measures the local spin of the fluid. In this helical flow, every tiny parcel of fluid spins around its own center at the exact same rate. Demo comparison. Rigid body versus irrotational motion. A helpful way to visualize this is by comparing two different types of swirling motion. Rigid body rotation. In our helical flow, the fluid behaves like a solid spinning cylinder. Every part of the fluid rotates at a uniform rate, meaning a tiny paddle wheel placed anywhere in the flow would spin at the same speed. Irrotational vortex. In contrast, some whirlpools, like water going down a drain, are irrotational. While the particles still orbit a center, the individual fluid parcels do not spin around their own axes. In that case, the particles closer to the center move much faster than those further out, creating a shear effect that is absent in our rigid body helical flow. The global perspective, momentum, and the off-center effect. When we examine a specific cubic section of this fluid located away from the center of rotation, we discover interesting global properties. Total momentum. Even though the fluid is spinning, it possesses a net momentum, a total bulk movement. Because our study area, the cube, is not centered on the axis of rotation, the spinning motion does not cancel itself out. Instead, the fluid appears to have a net push in two horizontal directions and a strong, uniform movement in the vertical direction. Angular momentum and the lever arm. The total spin energy, or angular momentum of this cube, is also affected by its position. There are two main factors at play. The primary spin. The strongest component of the spin is aligned with the vertical axis, as the fluid is naturally rotating around it. The orbital tilt. Because the cube is hanging off to the side of the rotation axis, its upward movement creates an orbital effect. This is similar to a spinning top that is also moving sideways. The total momentum vector leans, or tilts away from the vertical. Ultimately, this helical flow presents a fascinating rigid body paradox. On a local level, the fluid is remarkably simple, with every point spinning like a tiny, identical top. However, on a global level, when viewed through the lens of a specific off-center cube, the motion appears complex and asymmetrical, with tilting, momentum, and orbital energy created simply by the cube's displacement from the center of the spiral.